So we're going to start with sedimentary rocks. Just in terms of the rock cycle, I just want you to realize that 5% of Earth's crust is sedimentary rock. That's a pretty small percentage. However, 75% of Earth's surface is sedimentary rock. So on the surface, which is where the human population lives, 75% of the rocks that you actually walk on is sedimentary. So sedimentary rocks are fairly important. It's important to note that any of the three types of rocks can actually be weathered and eroded. So you can weather and erode a sedimentary, an igneous, or a metamorphic rock. So that's one thing that's really important that you understand up front. You need to know the difference between weathering and erosion. So you could take any rock and you can break it down into little tiny pieces, which we call sediment, and that process is called weathering. So I want you to know that weathering is the breaking apart of other rocks into little pieces called sediment. It can be done by physical means, like a glacier bulldozing across the ground, or a wave slamming into a rock, or water getting into the cracks of a rock and freezing and expanding, or a river, a raging river flowing down a hillside. They're all physical means, or it also could be like chemical means in terms of, like, say, acid precipitation and its effect on rocks like limestone or dolomite. So weathering can be physical or chemical. Once you've created that sediment, then you need to move that sediment or transport that sediment, and that's what we call erosion. So erosion is the movement of sediment, and that can be done by glaciers or running water or wind or the oceans. They're basically different erosional agents that can do that. Eventually, all of that sediment stops, and when sediment stops, we call it deposition. Most sediment will actually stop in a water body. However, there are some cases where that is not the case, for example, in a desert. So I just think about sand dunes in a desert where the wind is blowing the sand and the sand eventually gets deposited, forming dunes, and naturally that's not underwater. So the biggest, most important thing about sedimentary rocks that you got to understand, which is a part of the rock cycle, is how you actually go from sediment to sedimentary rocks. And so you're actually taking loose sediment and you're turning it into a sedimentary rock, and that process is called lithification. Lithification, though, can be further broken down into two what we call sub-processes, one being compaction and the other one being cementation. It's important for compaction that you just simply realize that the compaction comes from the sediment being more and more buried. So as the sediment gets more and more buried, which is typically because of more sediment being loaded on top of it, the pressure gets higher and the sediment grains get closer and closer and more compacted together. In that particular case, the space between the individual sediment grains gets less, and we call that space porosity. So as you get more compaction, porosity typically gets less and less. Normally, when the porosity gets less and less, the connections that actually go from the open spaces, which we call permeability, that also gets less and less too. Cementation is the gluing together or the sticking together of the sediment grains. And they use the word cementation, and I guess it's a good word to use because you guys understand what cement means, but it's also bad because you guys think of cement as being more of a human-made creation that you can buy at local hardware stores, whereas I want you to think of cement as being a natural process. And so a lot of the minerals that we've already studied in this course, like quartz, for example, quartz can be a cement, hematite can be a cement, calcite can be a cement. So those cements actually get in and glue the different sediments together as they get more and more compacted. So if you were to look in this particular diagram, what you'll actually see is a cool little diagram. You can see the little individual sediment grains. So, for example, these little things right here, just kind of shading them here, these are the individual sediment grains. You got to be careful, though, because we don't know what this picture is. Naturally, it's just a little sketch, but are they gravel size, are they sand size, are they silt size, or mud size grains? I don't really know. They look like they're sand to gravel size grains, but it could also be viewed through a microscope, and as a result they could be mud size grains. So just keep that in mind. Irregardless of the type of sediment particles it is, if you look in between, the red indicates the natural cement that's actually used to glue those sediment grains together. This would not be a good type of rock for oil and gas, because all the pore spaces in between the grains where oil and gas would typically be stored is actually filled up with the natural cement, in this case the red color, and as a result we would call this rock very tight, and as a result not suitable for oil and gas. So naturally, the more compaction that you get, the tighter those grains are going to be together. So you're going to reduce your porosity and permeability, and then the amount of cement that's actually going to be in there is also going to either reduce or increase the amount of porosity and permeability, typically reduce. So just some rocks here that we have. So coal is a sedimentary rock, but it's organic. Breccia is a sedimentary rock and it's clastic. It's made of gravel, just like this one's made of gravel. The difference being that Breccia got angular gravel and conglomerate got rounded gravel, and we'll talk about why later. Sandstone is a clastic sedimentary rock, just like Breccia and conglomerate. Sandstone is made of sand. Over here, shale is a clastic sedimentary rock made of mud, and siltstone is a sedimentary rock made of silt. These two down here, they belong to their own category. They belong to the chemical category, and a specific type of chemical category called evaporites. So gypsum and rock salt form as a result of the process of evaporation, which naturally gets help from the sun, evaporating the water. In this particular case, I just want to point out that gypsum is a mineral and gypsum is also a rock. In this case, halite was the mineral, and now rock salt is the rock. Limestone in this particular case looks like compact limestone. So compact limestone is a chemical sedimentary rock. In this case, it forms from a precipitate, just like dolomite is a chemical sedimentary rock, which also forms from a precipitate. Calcareous is basically cemented shells and skeletons of once living creatures, so that calcareous would be an organic or biochemical sedimentary rock. Chalk is made of microscopic animals, so that would be a biochemical sedimentary rock. So there are the three classes of sedimentary rocks. It's clastic, chemical, and biochemical. And so we've listed out the ones that are clastic, and it's important that I point out that clastic sedimentary rocks are different from each other based on particle size. So mud size versus silt size versus gran size, sand size versus gravel size. And also too, they pointed out in here particle shape, just because if it's gravel and it's rounded, you're going to get conglomerate, and if it's gravel and it's angular, then you're going to get breccia. And then the chemical sedimentary rocks, so as you can see, we had the evaporite category, which is your rock salt and your gypsum. I just wanted to have a couple words about sylvite. Sylvite is very similar to rock salt. The only difference is rock salt is NaCl, whereas sylvite is KCl. That's the only difference. If you have a chemical process going on called precipitation, that's where you would get your compact limestone. There's also limestone that you would get in the walls of a cave, and typically it precipitates from a freshwater solution, and we give that special type of limestone a term called travertine. And then there's also dolomite. So dolomite, I like for you to think of dolomite similar to limestone, except limestone is more calcium carbonate, whereas dolomite is more magnesium carbonate. And if you go to a place like Alberta or Saskatchewan or British Columbia, where there's a lot of oil and gas is actually found in limestone and dolomite out there. In terms of biochemical, we have coquina, which is all the cemented skeleton shells and parts. We have chert, which is basically a really hard rock made of quartz. Excuse me. The microcrystalline quartz has a link with organic creatures. And we also have coal, which came from plant material. We also have coral limestone, which is a different type of limestone. This limestone is actually created by living things. And we have chalk, which is made of microscopic animals. So these are the three different classes of sedimentary rock. So one of the biggest things that I need you to know is that grain size, and also be aware, because on the public exam they may say particle size. So all that's about is like mud versus silt versus sand versus gravel. So it's actually grain size. The other difference is grain shape. So if we're talking about conglomerate, it's rounded, whereas if we're talking about breccia, So yeah, so if the grain shape is actually rounded, then you get conglomerate, whereas if the grain shape is angular, then you typically get breccia. Sorting, you can get different types of sorting. Just think of like the different sediment sizes and how well they're sorted. If they're extremely well sorted, then they would all be gravel, or they would all be sand, or all silt, or all mud. And then that works all the way down to like moderately sorted to poorly sorted. In terms of the cement that you would actually get, we talked about like quartz cement, calcite cement, and iron oxide cement like hematite. The two big words, porosity is all the amount of open space in a rock, and permeability is how well those open spaces are actually connected. So here's a cool little graphic. All it does is just basically give some numbers and measurements to the different sizes of particles. So clay, which is basically mud, silt is a little bit bigger, sand is a little bit bigger, and then you get into your gravel. So for gravel, there's actually granules, which is missing from this diagram, and then pebbles, and then cobbles, and then boulders. If you were to consider like a river got a pretty high velocity. So a river's coming down, and a river is able to bring sediment of all different sizes. The minute when that river hits a water body like a lake or a pond or even an ocean or a sea, the velocity of the water drops. And the minute when the velocity of the water drops, then that water doesn't have as much energy anymore, so it can't any longer carry the larger particle sizes. So what it does is starts dropping off the biggest ones, and then as you go further and further away from where that river meets the body of water, the particle size will get smaller and smaller and smaller. And we actually call this horizontal sorting. And so if you were to look at this little schematic here, this is your high velocity. So this is where the river is going to first drop out your biggest particles like your gravels, and then your low velocity is going to be way over here, more horizontally farther away, where your particles are going to be smaller. So naturally that's your mud, which turns into shale, and silt, which turns into siltstone, and sand, which turns into sandstone. And then over here you have your gravels. And if your gravels are really close, then they would probably be more angular, whereas if they're a little further away and they've banged into each other a few times, the edges kind of got wore off and it's more rounded at that particular point. But typically the roundness of the grains increases as you get further and further away from where the rocks were actually. Where would you typically find clastic rocks? Well, we said in rivers and streams, and that's typically where you'd get your conglomerates and breccias, sandstones and siltstones and shales. In a lagoon, which is basically, most lagoons are typically fresh / salt water, real quiet environment, usually on the other side of a beach from the ocean. You would get some siltstones and shales. Along a beach, you could get more sandstones and conglomerates. And then out in the deep oceans, you get what we call turbidites. And turbidites are pretty high energy. I like to think of them like avalanches, but instead of snow, I like to think of them as like underwater avalanches of sediment. And really, you can get all the different clastic ones there, because once the avalanche of sediment is done at the bottom of the continental shelf, typically what happens is the sediment sorts itself out, not horizontally but vertically, and what happens is you actually get your gravels at the bottom, then your sands, then your silts, and then your muds. In more the shallow marine environment, so we're talking salt water, relatively shallow, kind of like just close off the coast of Newfoundland, you would get more of your gravels, sands, silts, and muds as you kind of went out there. So here's kind of a picture of some of them. So at the top left, you can see more of a braided river, and bottom left, you can see more of a meandering river, and top right, you can see more of a beach, and you can actually see the loose sediment there of gravel size. Actually, as you go out into the water, the sediment seems to be more smaller, kind of more of a silt or a mud. And then your shallow marine, which is in the salt water, but light can definitely penetrate through, and that's why you can get some life at the bottom. These turbidites that I talked about, it's kind of really cool. A lot of turbidites, sometimes happen on their own, and sometimes they actually are triggered by earthquakes. And we've had a few over the years off the coast of Newfoundland at the edge of the continental shelf. Now, our edge of our continental shelf is a long ways out. Like, we're talking like 350, 360 kilometers out. And we don't really know where the sediment is building up, but eventually the sediment can't take anymore, and it just falls down the continental slope all the way down to the continental rise. And these are really, really fast-moving, high-energy turbidity currents, consisting of gravel and sand and silt and mud in a big mixture. And then when it gets to the bottom, it settles out, and it settles out in a very vertical manner. So if you were to look at this diagram, On the right, you can see that there was 1, 2, 3, 4 different turbidity events that took place. And in this little schematic, you can see that as you go from the bottom of one, you get your gravels, and as you go up, you get your sands, and you get your silts, and you get your muds. And that's what we call graded bedding or vertical sorting.